RankNet learns from document pairs. ListNet can optimize the entire search list as one training target. You'll train a ListNet ranker on grouped result lists and compare whole list NDCG against pairwise RankNet. I'm Professor Pi, teaching AI foundations with simple Python. Think about a search page. A user types a question and sees several results together. They do not experience isolated document pairs. They experience the order of the whole page. A useful answer at rank 1 feels very different from that same answer at rank 5. Pairwise ranking teaches a model which document should beat another. That is useful, but it can miss the shape of the complete ranking. ListNet instead treats every candidate for one query as a connected list. It learns which documents deserve the most attention within that list. We will build a small PyTorch example with grouped search results. Each group represents one query and its candidate documents. The model will turn document features into scores, then learn to place more relevant documents higher. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We first need data that preserves which documents belong to the same search request. This snippet builds the smallest grouped ranking dataset we can use in PyTorch. Pairwise rankers often flatten the problem into document pairs, but ListNet needs to see the documents that belong to the same query as one list. The tensors X and Y hold document features and relevance labels, while QID marks which query each row belongs to. Groups uses torch.where, so later snippets can slice one query's candidate list at a time. The printed output confirms we have two query lists, and the first one contains 3 documents, which is the unit ListNet will train on. Now that the candidates stay grouped, we can turn one full list into a learning signal. This example turns one query list into the ListNet training signal with PyTorch. Instead of asking whether document A beats document B, ListNet loss converts all relevance labels into a top 1 target distribution with torch.softmax. Higher relevance receives more target probability, so the model is encouraged to put that document near the top. The model scores stay as raw logits, and f.log softmax gives stable log probabilities for the predicted list distribution. The dot product, x groups 0, at w, is just a tiny linear score, so the loss has something concrete to judge. The output shows the current score picks document 2 and pays a visible top 1 loss because that whole list ordering does not match the relevance pattern. That whole list target becomes clearer when we place it beside the familiar pairwise approach. This code contrasts the pairwise view with the listwise one using PyTorch. The same scores are split into 3 document pairs. Then margin measures whether the first document in each pair scored higher than the second. Pairwise says which pair direction is correct according to the relevance labels. And f.binary cross entropy with logits turns those margins into a RankNet style loss. This is useful because many engineers first learn ranking through pairs, even though search and recommendation screens display whole lists. The output shows this scorer gets every pair in the first query wrong, giving us a baseline to improve from. For more practical lessons in machine learning in Python, you are welcome to subscribe. A loss tells us what to improve, but we also need a score that reflects the ranked page users see. This snippet scores the model the way a ranked page is actually consumed. NDCG is a ranking metric that rewards relevant documents near the top, then compares the predicted order with the best possible order for that same query. The function sorts each query's documents by the predicted scores, rewards relevant documents near the top, and compares that result with the ideal sorted order. The torch.stack line applies that same metric to every group, then averages across query lists. This matters because pairwise accuracy can be informative, but it still does not directly say how good the visible top-to-bottom list feels. The output gives a whole list NDCG before value. which becomes the evaluation target for the training step. With a baseline measurement in place, the model can now learn from every grouped list. This example completes the tiny ListNet baseline in PyTorch. Model is a torch.nn.linear scorer that maps each document's features to one ranking score, and torch.optim.std updates its weights from the Listwise loss. Inside the loop, S contains all document scores, but loss is computed per query group, so each softmax only compares documents from the same result list. That boundary is essential. Documents from unrelated queries should never compete in one probability distribution. The learning rate, LR, controls step size. Increasing it can move faster but may overshoot, while decreasing it is steadier but needs more iterations. The output shows list NDCG after training, so you can compare the trained whole list ranking against the earlier baseline. In a production search system, this scorer usually runs after a fast retrieval stage has found a manageable candidate set. Retrieval may use simple text matching or embeddings to find possibilities quickly. A ListNet-style ranker then uses richer features, such as query document similarity, freshness, popularity, and document quality, to sort those candidates more carefully. ListNet is especially helpful when the order across the full result page matters. Pairwise RankNet can still be a strong choice when pair labels are easy to collect, or when your training pipeline already creates reliable comparisons. In either case, keep evaluation grouped by query. A ranking metric across mixed queries does not describe a real user experience. This tiny example also has an important limit. The relevance labels are clean and the lists are very small. Real ranking data can contain noisy judgments, missing clicks, and many candidates. You may need better features, regularization, validation queries, and careful monitoring of NDCG on unseen lists. Try changing LR and watch how list NDCG after responds. Then, experiment with the feature values in X and see how a different scoring signal changes the learned order. What ranking topic would you like to explore next, such as click labels, better ranking metrics, or recommendation lists? Leave a comment and subscribe if you want more practical PyTorch lessons.